This is essentially a classification algorithm. So what does it mean to classify something? Any ideas? Sorry, you can. Yeah, okay, I get what you're saying. So you're saying, is it going to be A, B, C, or D? Is this item going to be A, B, C, or D? So, like for example, if you're taking a multiple choice test, you would say, I have a question and I want to say, is the answer A, B, C, or D? Oh yeah, okay. And so the goal of naive Bayes is to find the output that gives the highest probability. So for example, if I'm taking a multiple choice test and I say, I don't really know the answer, but I'm like 15% sure that the answer is A. I'm 55% sure the answer is B, 25% that it's C, and 5% that it's D. With just being a human, I'd probably say, okay, I'm most sure that it's B, so I'm just going to go with that. And that's exactly what naive Bayes would do. Naive Bayes also uses label data. So does that mean if I'm going to be given some set of data to start with, and for every data sample I have, I'm going to know what output, what classification that sample is associated with. So for example, let's go back to our multiple choice question example. If I'm given the question, I know what the answer is. I know that the answer is B or A or C or D. And then you may have seen this word Bayes here. And for those of you who have some experience with probability, you may have thought it had something to do with Bayes' theorem. And you'd be exactly right. We use Bayes' theorem to make the predictions. And the math is essentially the Bayes' theorem, based off of Bayes' theorem. Okay, so what is naive about naive Bayes? What is it? Why is it called naive? When someone says the word naive, like what is the first thing that comes to mind? Or what do you think about if I say some person is naive? Like what would you think about that person? Yeah. Yeah, okay, so they don't have information, maybe they make assumptions about stuff. They don't they make assumptions about stuff, and that's exactly why we say naive Bayes is naive, because it assumes conditional independence. So, but before we start talking about conditional independence, let's go into what independence is. So if I say independence, what do you think that means? If I say two things are independent, what do you think that means? Anyone? Okay, freedom, like, yes? Exactly. They don't, one thing doesn't affect the other thing. So you're exactly right. Two events don't influence one another. So let's say I have two events. Event A is there's bad weather in Alaska, and event B is it's my birthday. It's not my birthday, but it's fine. Here's my birthday. Are these two events independent? Yeah. Why would you say that? They're not related. If it's my birthday today, if there's bad weather in Alaska, that doesn't change that it's my birthday today. If it's my birthday today, that doesn't affect the weather in Alaska, hopefully. Let's take a new event. So this diagram is just to kind of visualize things, but we have two events. There's traffic outside, and I'm carrying an umbrella. Would you say these two events are independent? Okay, so yeah. So like if I think about this, if I wake up, I go outside, and I close my eyes, I just walk outside, I can't see anything, and I can't feel anything. But I hear that there's a lot of traffic. I might make some assumptions. I might be like, okay, maybe it's just a bad time. Maybe it's like rush hour and everyone's going to work. I may also say that, isn't it a possibility that there's bad weather and that's the cause of the pileup? Isn't that a possibility? That when it's raining, there is more traffic, right? So I could say that, yeah, these two can be dependent. So does that make sense? Okay, so, but now let's introduce the idea of conditional independence. So what if I add a third event? I say, I'm going to add this idea that it's raining outside. So now I'm going to say that I'm going to hold rain constant. I'm going to say, I know it's gonna rain. Like I know it's raining right now. I can hear the rain, I can feel the rain, whatever. I know it's raining. I also look outside and I see there's traffic. And is this traffic gonna change the fact that I'm gonna take my umbrella? No. If it's raining, I'm gonna carry my umbrella whether or not there's traffic outside. So because we kind of based both of these decisions on this variable here, we can say that traffic and carrying an umbrella. So initially we said that they are dependent because if there's more traffic outside, you could say that there's bad weather and you'd be slightly more likely to take an umbrella. But now we know that it's raining, and we're fixing this idea that it's raining, and now these two events have nothing to do with each other. Does that make sense to everyone? Okay, so because of this, we can say that carrying an umbrella and our traffic are conditionally independent. So we understood like the logic behind it, how this idea of conditional independence would apply in like a real world setting. But let's kind of define it more formally. So we'll say when conditioning on an event, we'll call it C, events A and B are independent. So in our rain example, when conditioning on rain, our events traffic and carrying an umbrella are independent. So mathematically, we understand this logically now, but we need to represent this mathematically. So mathematically, we would say that we would take this notation here. We'd say that two events, A and B, given, so this line here means given. So A and B, given a third event C. And if they are conditionally independent, by probability rules, we can say that it equals to the probability of A given C times the probability of B given C. So we can say the probability of there being traffic and me carrying an umbrella are given rain. And then we can say that that is equal to the probability of traffic given the rain and carrying an umbrella given the rain based on this formula here. So just a quick summary of what we've gone through so far. We said that naive Bayes assumes conditional independence, and we represented conditional independence by this formula here, where if I have two events, A and B, given a third event, C, I can break that down into the probability of A given C times the probability of B given C. And with our rain example, we said that the probability of traffic and carrying an umbrella, given that we know there's rain, is equal to the probability of traffic, given that we know there's rain, times the probability that you're carrying an umbrella, given that there's rain. Okay, so any questions up to this point? Okay. So okay, we went over the naive part, so we know why naive Bayes is naive because it assumes conditional independence. So now let's go over the Bayes part, and this is where kind of more of the math comes out. So going forward, when we say big X, we're going to be referring. We can also represent this as this notation here, the set of all inputs. And when I say Y, we can say that that is the output. Let me just give a quick example. So for example, if I'm saying that X is the inputs that are a housing configuration or a housing layout, I can say X1 will be the number of bedrooms, X2 will be the number of bathrooms, X3 will be the square footage, and all the way till Xn, where n is going to be the number of inputs. So if I just have three inputs, number of bedrooms, number of bathrooms, and square footage, then my n would be 3. And then my output is, say I want to say, like, I'm given this configuration. I know it has so many bedrooms, so many bathrooms, and is this many square feet. I'm going to know, is this a house or is this an apartment? So my outputs would either be house or apartment. Okay. So remember, we say that naive Bayes, the goal is to find the output that gives the highest probability. So if I'm taking a multiple choice test and I'm not really sure what the answer is, what is one way I'd go about trying to find the correct answer? Yeah. But how would I have to start? Like, if I just have the question and I have all the possible answers, how do I know that this is likely not an answer? Like, what would I have to do with all the options? I have option A, B, C, and D, but I'll have to know what A is, know what B is, know what C is, know what D is, right? So, how would I go about approaching solving the problem? Yeah. Yeah, so you go through each output essentially, right? And you say, um, like you can, I guess you don't really do this when you're taking a test. You'd say, I'm this much sure. You could say I'm this confident that the answer is A, this confident that the answer is B, C, and D, and then you'd probably just take the highest one. If you're pretty positive the answer is B, you'll go with B, right? Does that make sense? Yeah. So that's what naive Bayes does. It essentially takes each possible output and says, how confident am I that this is the output? And then it'll take the output that it's most sure of. So we can represent this mathematically as a probability of y given, so the probability of an output given the input. So for all my possible outputs, I'm going to find the probability that that is the correct output. So for example, if I'm going to say my house and apartment example, I'm going to find the probability that my configuration is a house. I'm going to find the probability it's an apartment, and then I'm just going to take the higher of the two. And so what does this actually break down into? Well, it breaks down into this right hand side here, and this whole formula is Bayes' theorem. So this whole formula is what we're gonna base our calculations off of. So we're gonna essentially it's gonna be the probability of an output given some inputs equals the probability of the input given we know what output we're going off of, the probability of that output occurring, and divided by the probability of the input occurring. And we'll go through each of these components one by one. So let me just give like a quick example about this. So for example, let's go with the housing thing. The probability that my configuration is a house is equivalent to the probability that I have that configuration given that it's a house times the probability of it alone being a house based on the data I'm given, divided by the probability of that configuration being true. So again, let's take a look at just this right-hand side. Specifically, we'll look at this one first. So this is essentially saying you're fixing your output. Like I know my configuration is a house. I'm trying to find the probability that it has 2 bedrooms and 2 bathrooms and is like 1,000 square feet. This segment here is saying I have a data set. Because remember, naive Bayes uses training label data. So I have my data set, and if I have my data table and I put my finger somewhere on the data table, what is the probability that I put it on a sample that is a house? So let's take this data table here. So we have 2 inputs that belong to output A, and we have 1 input that belongs to output B. So if I were just to randomly pick something from this table, what is the probability that I would pick output A? 2/3, exactly. And how do you get that? Yeah, so I'm just looking at how much I have in total and how much of it belongs to output A. And then if I were to ask you, what is the probability that I pick output B? What would you guys say? 1/3, because there's only one B out of 3. Okay. Before I go in depth into this, just remember that this computation is done for each possible y. So remember, I'm doing this for I'm doing this calculation to find out if my configuration is a house and I'm doing it to see if it's an apartment. And I'm doing these separately. So first I'm trying to find out first I'm doing this calculation to find out what is the probability that my configuration is a house, and then I'm going to do it for what is the probability that my configuration is an apartment. In both of these calculations, my input x doesn't change. So if I were to say that what is the probability that my configuration of 2-bed, 2-bath, and 1,000 square feet is a house, I'm also going to say what is the probability that my 2-bed, 2-bath, 1,000 square feet configuration is an apartment. So this value doesn't change across my calculations. So if I have two fractions where the denominator is the same, so you have 3/5 and 4/5, do I need to look at the denominator? Is that relevant in finding out which one is smaller than the other or which one is greater? No, I just need to look at the numerator. And I can say 3 is less than 4, so 3/5 is less than 4/5. So to save on computation, we can just ignore this. And we can simplify our Bayes theorem down to this equation here. So we know what we understand what this is. We understand what this component here is. So now let's break down this P of big X given Y. So remember, when I say big X, I'm just referring to the set of all inputs. So if I'm saying the configuration example, I'm going to say X1 is the number of bedrooms, X2 is the number of bathrooms, X3 is the square footage, etc. And because of that, because X is just equivalent to the set of like X1, X2, X3, instead of saying P of big X given Y, I can just say the probability of X1, X2, X3 till Xn given Y. I'm not changing anything, I'm just rewriting it. And then remember from our naive assumption where we said because if A and B are conditionally independent, given C, we can break the equation down to this. And we also have our probability in this form now, our X given Y, our big X given Y in this form now. So we can just apply this equation to this equation here and rewrite this probability of X1, X2, X3 given Y as the probability of X1 given Y times X2 given Y all the way to Xn given Y. So again, I can just say the probability of big X given Y is just the probability of X1 given Y, X2 given Y, X3 given Y till Xn given Y, where again, N is a number of inputs. So for example, like bedroom, bathroom, square footage, N would be 3. Any questions now? Yes, these are multiplied. Yeah, that's a good question. We multiply these probabilities together. Yes. Given Y means I'm holding Y fixed. So I'm going to say, I know that this is a house. I know that whatever I'm talking about is a house. So the probability of some inputs, given that I know that it's a house. Does that make sense? Any questions? Okay. So now that we know what P of X given Px given Y is, we can kind of connect this back to our simplified version of Bayes theorem. And we can get this equation, this more broken down equation of Bayes theorem here. So instead of saying that the probability of a configuration the probability of our configuration being a house is equivalent to P of X given Y times the probability of Y, I can say that the probability that my configuration is a house is equivalent to the probability that I know it's a house, or the probability that it has 2 bedrooms, given that I know it's a house, times the probability that it has 2 bathrooms, given that it's a house, times the probability that it's 1,000 square feet, given it's a house. And then I'm just moving this, the probability that it's a house, given my data, or using my data, on tagging it on there. Any questions? Wait. So we know what this is. We know what this is. And we've simplified our P of X, Vic X given Y into this. But how do I calculate this value here? And so this is where we bring in kind of a probability distribution. So at a high level, the main thing that you kind of need to understand is, well, you would be using a bell curve to find that value. So when you want to find the probability of some x given y, you just take, so say your x is 5, so you'd take your value 5 and find out where does it map to on the curve. So if my input's 5, it probably maps to like 0.07-ish. And this is known as a Gaussian distribution, but you can also call it a bell curve or normal distribution. So this is the equation for the bell curve, but you don't need to get bothered by this. Really, what you need to understand is just the 3 components here. So you just need to understand that this mu is the mean, this sigma is the standard deviation, and this xi is going to be our input value. And when we have to, so going forward, we're just going to use this notation here. We're not, this is the equation. If you want to write it down, you can, but you don't need to get overwhelmed by this at all. We're just going to refer to it by this. But when you calculate the mean and standard deviation, you're going to do that for each input and for each output. And we'll just take a look at an example to see how you would go about doing that. So here's my example. The one we've been going over so far, classifying a house configuration as a house and apartment, where we're just gonna have two inputs, number of bathrooms and number of bedrooms, and the output will be, is this a house and apartment? So to find that, like, how am I gonna create that normal distribution? Remember we said we need to find the mean and the standard deviation for each input and for each output. So using my data, I need to know what is the average or the mean number of bedrooms in a house, and what is the mean number of bedrooms in an apartment? What is the mean number of bathrooms? Mean number of bathrooms in an apartment and a house, and mean number of bedrooms in a house and an apartment. And then we also need to find the standard deviation. Is this any questions so far? Okay.
Anything that people want us to go back over?
Oh, yeah.
Just re-clarify. Any confusions? You don't have to necessarily have a well-formulated question.
So Bayes' theorem was, our simplified version of Bayes' theorem was this.
All of the slides and stuff will be posted on Discord in the meeting.
Yes. Yeah. Good question. So yeah, we did divide it by P of X earlier. But remember we said that X remains, yeah. Remember we also said that P of X remains the same across the calculations. So if I was trying to calculate the probability that my configuration was a house, or if it was a house or an apartment, first I'd say, is this 2-bed, 2-bath configuration a house? And then I'd say, what is the probability that it's a house? And then what is the probability that it's an apartment? And in both those cases, the idea of the 2-bed, 2-bath or my X stays the same. So it's basically like saying, I'm gonna do 3/5 and then I'm gonna do 4/5. So that 5 really doesn't matter if I want to just say which is bigger, which is smaller. That was a good question.
So to kind of reiterate, remember we said the goal is to figure out which has the higher probability. Is it going to be y equals 1 or y equals 2? Or in this case, y equals house or y equals apartment. That's what we're trying to decide. That's the end goal. And to do that, we look at this thing and we say y equals 1 given x. and y equals 2 given x, y equals house given x, y equals apartment given x. That is the end goal. But if you notice, these x's are both the same. So when we expand it with Bayes' rule, this is also going to be the same. This isn't going to change. And so essentially what we're going to have is, let's say that top part for y is 1 evaluates to 3. And then let's say the top part evaluates to 4 for the y equals 2. So then we have over p of x and over p of x, right? And we're trying to figure out which of these numbers is bigger, 3 over p of x or 4 over p of x. Does p of x matter? Do we need to worry about that? One way we can figure out which is bigger is we can just get rid of the denominator like this. And now figuring out which of these is bigger is going to be the exact same question. Does that make sense? And explain why we can drop the p of x? Cool.
Okay, so coming back, we were trying to figure out how to create that distribution for our data, and we know that we need to calculate the mean and standard deviation for each input and for each output. So if my inputs are number of bathrooms, number of bedrooms, and my potential outputs are house and apartment, I need to know the mean number of bathrooms for the house, mean number of bathrooms for the apartment. Same for the bedrooms, so mean bedrooms for the house and for apartment, and then the standard deviations. So standard deviation for bathrooms in a house, bathrooms in an apartment, bedrooms in a house, and bedroom in an apartment. And so let's kind of practice this with an example. So here's my training data. My potential outputs are house and apartment. Yeah, so this is made up. I have a house with 1 bedroom and 6 bathrooms, 2 and 5, 3, 4, 4, 3, 5, 1. Okay. So let's calculate the mean and standard deviation specifically for the house. So now we're just going to concern ourselves with the house, and we're going to look at both the inputs. So, and then we'll write down the Gaussian equation for like how we would take our mean and standard deviation and represent that equation. So just looking at this data table here, can someone tell me what is the average number of bedrooms? So that would be this row, bedrooms, this column here for a house. Yes. Yeah. 2, exactly. How do you calculate that? Exactly. You took 1 plus 2 plus 3, you got 6. And because there were 3, the sample space was 3, so you divide by 3 and you got 2. Can someone tell me the mean number of bathrooms in a house? That would be this column here. Yeah. 5. How do you get that? Yeah, 4 plus 5 plus 6 divided by 3. Good job. And then I want to ask you guys to calculate the standard deviation, but this is the mean, 2 and 5, and the standard deviations were 1 and 1. And then now we can represent our Gaussian equation. So remember, we just take our input, which we don't know yet. So we're just going to say it's x1. We're going to leave it as x1. And then our mean for this particular input and output, for the particular input of bedrooms and particular output of house, the mean was 2. The standard deviation was 1. And then for the number of bathrooms, we have our distribution for the mean number of bathrooms was 5 and the standard deviation was 1. And this is specifically for the house. So does that make sense to everyone? Any questions, clarifications, anything? Comments? Okay. So now let's do the same thing, but for an apartment. So who can tell me the mean number of bedrooms in an apartment? Yeah, 4. So 3 plus 5 divided by 2, you get 4. And then what about for the number of bathrooms? 3. 4 plus 2, 6 divided by 2, 3. And then again, I will not ask you to calculate standard deviation, but here's the mean, standard deviation. And then the same idea. Right now our x is just a variable. So we'll just write it as x. Our mean is 4 and our standard deviation is 1. And then same thing here. Our x is just an input. So we're just going to leave it as x. Then the mean is 3 and the standard deviation is 1. Any questions on how we derive this or anything so far? Okay. So this is just compiling everything into one space. So we have the equation for the house and number of bedrooms, equation for house and number of bathrooms, equation for apartment bedrooms and apartment bathrooms. Okay, so coming back. So now we know that this was our simplified Bayes theorem equation. And we know how to represent each of these x1 given y, x2 given y, x3 given y. So I'm going to be multiplying a bunch of probabilities together. And probabilities are always between 0 and 1. So what could go wrong if I multiply a bunch of very small, close to 0 numbers together? Yeah. Exactly, you get basically 0. And that's not going to be useful in making our classification. So what we can do is quick log rule. So if we're multiplying two numbers and we take the log of them, we can just take the log of the individual components and add them together. So we're going to apply this logic with our simplified Bayes theorem equation. So instead of multiplying all these probabilities together, we're just going to take the log of each of them and add them together. And at that point, we're not really going to get a probability between 0 and 1, but we're still going to maintain that idea of this is more likely than that in terms of the comparison between the outputted values. Yes, it is log of p of x. We didn't write that there just because it might get a bit confusing. But essentially, it is the final output is technically going to be log of this.
But that doesn't really matter because if you're taking two values, and one is greater than the other, the log of both those values will maintain that. So 0.5 is greater than 0.2. Log of 0.5 is still going to be greater than 0.2. And that applies anytime. So we can apply this log rule, and because we're just comparing them, that's still going to hold and everything will be okay.
Okay, so it's quick summary. So far we've said that naive Bayes assumes conditional independence. We've made our simplified version of Bayes theorem. And we said that we can model this P of x1 given y, P of x2 given y, etc. by this distribution here. And to calculate this distribution or to create this distribution, I guess, we can calculate the mean and standard deviation for each input and for each output and for each input. Okay. So let's take a quick coding break. Actually, we'll for now we'll go into an example. So yeah. So remember that again. This is our equation that we kind of simplified. And let's go through this example where I have some data on how many hours a student slept, how much water they drank, and whether they passed or failed. And what I want to do is if I'm given a new student, like the number of hours they studied and the hours they studied and the amount of water they drank, I want to know if they're going to pass or if they're going to fail. So what do we need? Okay, I guess I gave it away, but we need to know the probabilities. We need to know everything here. So we need to know the probability of each output. So the probability of the P of Y's, the probability that they would pass and fail. And I would also need to know my probabilities of that X given Y. So the probability of X1 given that they passed and X1 given that they failed and X2 given that they passed and X2 given that they failed. So based on what we've learned so far, can someone tell me what is the probability of passing? Yeah. 2, exactly. And how did you get 2/4? Yeah. So again, we just looked at this column and we said, if I put my finger somewhere on this table, what is the probability that I'm going to put my finger on a pass? And then what about for fail? It's also 1/2. Good job. Okay, so now let's calculate this nice little probability of x1 given pass and fail. So first, remember, we need to calculate the mean and standard deviation for each input and for each output. So first, let's look at the mean and standard deviation for passing. So I've just put this down here. In this, we're just going to refer to it as x1 and x2, but x1 is the hours studied and x2 is the amount of water they drank. And this is my data. So what is the mean for x1, or what is the average number of hours a student who passed studied? Yeah, sorry, 5. Yeah. How'd you get that? 10. Yeah, exactly. 10 plus 0 divided by 2. And then what about for the amount of water? Yeah, 3. 2 plus 4 divided by 2. And then standard deviation is 5. Not gonna ask you to calculate that. And then we're gonna do the same thing with the students who failed. So I think you guys have done this a bunch by now, so we're just gonna go through it really quickly. The average number of hours a student who failed studied is 3 plus 7 divided by 2, and the average amount of water they drank was 7 plus 5 divided by 2. So 5, 6, and then standard deviations are 2 and 0.5. And now we just need to represent it in this form right here. So I know my means and standard deviations for each of my inputs and each of my outputs. And I want to calculate the probability of x1 being some value given that they passed. And can someone tell me like what boxes, I guess it's already here, but what boxes would I, or like what ideas would I use to get this representation? So I'm trying to see the likelihood that I'm trying to see the probability of the feature or the input x1. So x1 and the output is that they passed. So can someone tell me where is this 5 and 5 coming from?
Just we'll give the laser pointer and just point to where on the tables they're coming from. So raise your hand if you want to do that. If you have a guess as to where these two numbers from these tables are coming from.
Or yeah.
I'll go ahead and pass it up so you're the microphone. So 3 numbers of those passed. But just the first one is the first row of 5 and 5. Yeah, correct.
Do I need that? Oh.
Moving on.
Okay, yeah. Or exactly. So it would be 5 and 5 because we're looking at x1. So that would be somewhere along this row. And we're specifically looking at the output of pass. So it would be in this table. So this would be 5 and 5 from here. And same with 3 and 0.5, 5 and 2, and 6 and 0.5. Does that make sense? Any questions, confusions, clarifications, anything? Okay. So now I've just moved whatever we said over here down here, so it's all the same thing. So now we know the P of Y, so we know the probability of passing and failing. We know our x1s. We know the x1 given pass, x2 given pass, x1 given fail, and x2 given fail. And we just need to apply this into the equation. We just need to apply this into our equation. And when we're given like a input, we can solve for that input. So let's try this. Let's classify something. So I'm going to say that this student studied for 1.5 hours and they drank 1 gallon of water. So what are we? So I guess in terms of English, like what are we trying to find? Remember the task at hand was to figure out if a student is going to pass or fail. So in terms of just English, what are we trying to find? Yeah.
Given that they slept for exactly 1 hour.
Yeah. Yeah, exactly. Oh, so we're just trying to maximize this value. So what you said is exactly what it means in like English. This is what it was like the mathematical notation to represent it. So the probability that a student will pass or fail given this set of inputs. And so one way we can represent this is the probability that they pass given this set of inputs, that they slept for this many hours and they drank this much water. And then the probability that they would fail given that they slept for this long and drank that much water. And then again, I'm bringing back this equation. This is again the simplified version of Bayes' theorem. It's you've probably seen this 5 times so far, but this is the equation again. And because we don't need, remember here we had x1, x2 all the way to xn. We only have these two inputs of water and sleep. So we just have x1 and x2. And from the previous slide, this is again just from the calculations we did a few slides ago. I've just moved it over here. So we found out that for the input of sleeping, a student who passed on average slept for 5 hours and the standard deviation was 5. And for a student who failed, they on average slept for 5 hours as well, and the standard deviation was 2. And then I just do the same thing with my x2, which was the amount of water. So we found out that a student who we found out that a student who drank a student who the average amount of water that a student drank who passed was 3, and the standard deviation was 0.5, and then a student who failed drank 6 gallons of water, and the standard deviation was 0.5 too. Okay, so again, we're just taking again our simplified Bayes theorem equation. We're trying to find this value right here, and we have all of these components. So we're just trying to find, first we're going to start off with passing. We're just trying to find the probability that a student would pass given these inputs. And we know that this probability was modeled by this distribution. Again, we calculated that. We know that this probability was modeled by this distribution. And we said that the probability of y was 1/2. So we're just going to plug and chug all of these numbers. And when we do the calculation, we get that the value that you would get for a student who you would assume is passing is negative 5.08. Any questions here or anywhere from previous slides? The normal distribution was the one we had calculated earlier. So, yeah, or this one. So remember we said we calculated the means and the standard deviations for each output and each input, and then we just associated like each distribution with the probability. So we said that the probability of some input of the probability that a student slept for so many hours given that they passed was modeled by this because they on average they slept for 5 hours and the standard deviation was 5. Yes.
So just to clarify, each of these n of mu equals 5 or mean equals 5, standard deviation equals 5. Each of these, if we go all the way back, oh goodness, that's interesting. Hello. If we go all the way back to that curve, the bell curve, the standard deviation curve that we saw here, the n of the mean and the standard deviation defines the shape of this curve. And then that first variable that we plug in that we're trying to find given that mean and standard deviation determines where on the curve we're trying to find something. So the mean and standard deviation define the shape of the curve, and then the thing that we eventually get to that we're plugging in defines where on the curve we are looking. Does that make sense? Okay, cool. Sorry, I just wanted to clarify that. I'll go fix the slides. Yes.
Okay, and then this 1.5 here comes from the fact that we're dealing with x1. And then the one comes from x1, which is the hours slept, and then the one comes from x2, which was the amount of water drank. And we said that in our input, the person slept for 1.5 hours and drank 1 gallon of water. And we just do the same idea with the probability of failing. So we're trying to find the probability that a person fails given 2 inputs, so that they slept for so long and that they had that's 1 gallon of water. And then again, we just plug in the distribution we got for P of x1 given y, for P of x2 given y, and then the log, take our P of y, add this together, and then we get this value right here. So now we have two, we derived 2 values. We said that the likelihood they'd fail was associated with negative 23.48 and pass is associated with negative 5.08. And just looking at these 2 values, which is greater? Pass or fail? Is fail greater? Pass is greater, because remember we're dealing with negatives, so this would actually be greater. So we're going to say that the student would pass. Okay, does this make sense? Like, would we expect this? Well, let's look at this. So we see like our means are the same, so we can't, maybe comparing them to our input may not do that much good. But we see our the mean for the hour studied. But if we look at the amount of water that they drank, we see that the mean here is 3, the mean here is 6, and they drank 1 gallon. So are they closer to this or closer to that? Closer to pass or closer to fail? Is 1 closer to 3 or is 1 closer to 6? 3. So yeah, we can expect that because it's closer to one of our inputs. Our inputs are closer to the inputs with pass. We can expect that they would fail. They would expect they would pass. Okay, quick recap. Okay, quick recap. So naive Bayes, the goal is to maximize the probability and find the output that maximizes that is associated with the highest probability or highest value. We assume conditional independence, and as part of Bayes' theorem, we use a bell curve to determine these values, and we can represent the distribution by this, where mu is the mean, sigma is the standard deviation, and we have to calculate the mean and standard deviation for each input and for each output. Okay, so let's go to the code really quickly.
So we're going to go through the code really quickly, as fast as we can. There's only, I think, 6 parts for you guys to fill in. They're all pretty close together. They're all very similar. So we'll be able to get you guys through this a lot faster than the code for the previous one. But I just wanted to say that was a lot of math. I know we said that that AI in general doesn't require a lot of math. This is one of the very few ones that it's hard to do graphically, visually, et cetera, et cetera. And we do just have to use a fair bit of math to explain naive Bayes. But one of the cool things is naive Bayes is the very first stepping stone to who here has heard of ChatGPT, transformers, LLMs, all of that fun stuff that we think of as AI right now. I hope most of you guys have heard of ChatGPT, or maybe not hope, but I assume most of you guys have heard of that. Naive Bayes is the very first step into understanding all of that. So if you're curious about that kind of stuff, understanding naive Bayes is going to be your first step. It's incredibly complicated, it goes much further, but this is the first thing to understand if you want to think about understanding. And maybe it can give you a bit of an understanding about how maybe it could start to work. maybe not necessarily from this, but it's the beginning of that stuff. And then also, I wanted to mention next week we're going to be covering k-means, which is a lot more graphical, a lot more visual. We talk about it with different colored circles and just figuring out what color a circle is based on the circles around it. It's a lot more visual, it's a lot more graphical. But I also want to say Rushika did an amazing job describing naive Bayes. I know it's very mathy, but this was one of the most simple explanations of naive Bayes that I've seen. And I wanted to say, before we move on to the code, thank you so much. That was really amazing.
Okay, so yeah, thank you for that. Also, so the code is tinyurl.com/sky, SCAINB.
Raise your hand if you are having troubles or need help or still getting the code set up or need the link still.
You will need to go to File and save a copy. So I believe you are on View only with the, if you just go directly to this link. So make sure you go to File, save a copy, and work on your copy. Okay. So remember we said that we needed to calculate the probability of an event happening just looking at our data. So with the housing thing, we said, I forgot the exact example, but okay. So let's take a housing thing. If we have four configurations to our houses, to our apartments, then the probability of there being a house is the number of houses over the total number of houses, or total number of configurations. So in our data set, we have a data set of flowers. So this is from the scikit-learn library, sklearn directly, library. And then we have these inputs of sepal length, sepal width, petal length, and petal width. And our outputs are the types of flowers. So it would be setosa, virginica, or versicolor. And we want to find the probability of if we just pick a flower at random, what's it going to be? So to find the probability, when we went over the example, we all said that it was going to be the number of that sample over the total number of possible, like the total number of samples. So we have a variable here that says the number of the flower, and we have a variable here that says the number of samples in total. So to calculate the probability of a flower, I'm just going to say it's the number of that flower divided by the number of samples. So I'll just fill in this first one here. And then I think it would probably be better to do all of them. So. Okay. And we also said that we need to calculate, in order to get that, find what distribution we're going to use, we needed to calculate the mean and the standard deviation. So here we're going through every output and we're going through every input. If you don't understand the exact syntax, that's okay. But just the idea, we're going through every output and then we're going through every input. And then we need to find the mean. So there is a Python function that actually helps us out with that. So we know we have all the samples. We just pulled all the samples that are associated with this particular output and this particular input, and we stored it in this variable here. So we're just going to take this variable. I'm just going to call mean and call standard deviation on it. And this is like a Python function that'll just calculate the mean and standard deviation for us. Okay. And then finally, we'll come back to our Gaussian equation. So we need to calculate the probability of something happening. And we said that we need to calculate the probability of some x given y. And we said that the way to do that was to create that Gaussian distribution. But how do we use that Gaussian distribution? Now remember that Kevin mentioned that we just take an input and we just plot it onto the x-axis of that graph. And then we find the y value associated with that x value. So because we already have, above we've declared a Gaussian function. So this function just does that big equation that I showed you that I said you don't have to worry about. This function here just does that. And so all we're going to do is we're just going to calculate the probability, we're just going to call this function with our mean, our standard deviation, and our input. And we're going to do that in our probability function. I called it P. Okay, so in terms of code, you all can go through, there's a lot of like syntactical stuff related to different libraries. And I believe it is, you can just go through the code on your own time. If you have any questions, also you can come up and ask, or like Discord, however you want. You can just go through the code. Any questions, you can just ask us. But this is kind of like the high level idea of how do I calculate the mean and the standard deviation, and then how do I calculate the probability. So I think the probability, this function here might be a bit confusing, so I'll just explain it one more time. So when we wanted to calculate the probability, like P of x1 given y, we needed to create that distribution. And in that distribution, we had to say that there's a mean, there's a standard deviation, and I'm going to put in some x value. So in this function here, all I'm doing is telling the Gaussian distribution what is the mean, what is the standard deviation, and what is the input value that I'm putting in. And I'm just going to call call the Gaussian function with that mean value, mean, standard deviation, and input value. So we can just run everything so far.
Actually, yeah, that's a good thing to point out though. If we have all the code done, which we filled in those 6 points, you can just do runtime, run all, and it will sequentially run every single cell and just do that all, so you don't have to keep clicking through and be like, oh, I missed this cell.
So this is an output of what the probabilities of each of our inputs, and then the mean and standard deviation for each of our inputs and each of our outputs. And then we have a classification function where we're just doing the sum of, oh, here I go.
Sorry. So we can go over like the rest of that notebook, but it should be explained in the text, and we don't want to keep you guys here too long. We want to get to the very last slide and stuff like that. So I'm gonna say, do you want to end it? Or
No. Yeah, that's pretty much it. Yeah, like you said, the code is explained in the notebook itself, so you can go through that. If you have any questions, you can ask us. Yeah, but for now, thank you for coming to this meeting. Here is our feedback form. So if you could fill this out, that would be great. That would help us improve lectures or meetings going forward. Just help. If you have any comments on like the structure, like how certain things were explained, feel free to comment that there. And that would really help us going forward.
Yeah, and so if you do like want to come to these meetings in the future and want to keep getting stuff from them, we're trying to tailor them to you. Last time there was only like 1 or 2 people who filled out the feedback form, and we do read through them and take the feedback into account. So it means if you fill this out, whatever you say, we're going to see and we're going to try to implement in the future. So, you know, very, very personalized. It's not just going to get lost. But yeah, thank you everyone for coming. Again, next week we're doing k-means, k-nearest neighbors, some classification algorithms like that. It's going to be a lot more visual. This one was a little more mathy, but I appreciate you guys for sticking through it, as it's incredibly helpful and useful in AI in general. And again, thank you, Rishika. This was an amazing presentation, and we'll be here if you guys have any questions, want to come up and ask them, or just raise your hand as people are leaving. But yeah, thank you so much, everyone. I'll see you next week. Thank you. Have a good day.